chapter 4. Chapter 4, we're going to continue on describing data. This time we're going to look at displaying and exploring data. Now, coming out of chapter 2, we actually looked at some of the graphical displays for summarizing qualitative and quantitative data. For qualitative or categorical data, we looked at bar plots. We looked at pie charts. And for quantitative data, now we're going to look at some some graphical displays for most parts for quantitative data. That's what these are for. In chapter 3, we looked at measures of central tendency. That was the mean, median, mode, deviation, and variances. So in this section, we're actually going to take a look at also another application of median and also quartiles in aiding us create some displays, visual displays of our quantitative variable. So the first of the series of quantitative plots that you're looking at, and by quantitative plots what I mean is that plots or graphs for quantitative variables. Okay, so the first of the series, we're going to look at dot plots, we're going to look at stem and leaf displays, and we're going to look at box-whiskers plots. Those three in this chapter. So first, beginning with dot plots, here I have an example of a dot plot for exam scores. These scores we actually looked at them before. Okay, in previous chapter when we talked about measures of central tendency, the actual data is in chapter 3. Okay, so now dot plots pretty much work like histograms, except there are at least a couple of usages of dot plots. One is to show the spread of data points. As you can see in this one, it tells me how spread out the data points are. One thing about the dot plot is that you're going to have as many dots as there are scores. So let's say if I count the number of dots here, 1, 2, 3, 4, 5, 6, 7, and 4 makes 11, 13, 15, 16, and 4, 20. So these are 20 data points. Okay, so we're looking at 20 test scores. With dot plots, of course, you can locate the minimum, you can locate the maximum also. It's harder to locate the mean and the median, of course, on these. Definitely not the mean, because for that we have to add them all up, divided by the number. But we can easily locate the minimum and the maximum. And again, importantly, we can look at the spread of these dots around a measure of central tendency. Okay, because that's one usage of it. And when the data set is large, the dot plot actually will play the role of a histogram. Okay, we looked at how to construct histograms earlier again in the previous chapters. So those are the two usages of dot plots to kind of get a visual sense of a spread of scores and also to look at the distribution of scores. Now, as a histogram, this one is not really informative. So the use of dot plot here would be to kind of get a feel for the spread or dispersion of data values. Okay, now this is what I mean by dot plots. Now for this one, it's aiding as a histogram. So you can see again the spread isn't that bad. The cluster of points are here. This is the dot plots of 160 test scores actually. So it's a bigger data set from which that upper data set, this one, was drawn from. Okay, so there you have it. Now, here's an example that's actually in your book. So this one actually looks at the number of employees at each of 142 Home Depot stores in the Southeast region. You see that? So you look at that distribution, it looks like kind of nice, symmetric, almost distribution, right? You don't get perfect symmetry with these, but you somewhat get of an impression of a symmetry here. Right around here is if you had few more dots, if you pick up maybe 4 dots here, let me see, 4 dots. If you take 4 dots from here and move them over here, then you get very, very symmetrical distribution. Very close to it, I should say. So anyhow, that's the other usage of dot plots. And Megastat and both Minitab, if you look at the video or watch the video from chapter 3, in chapter 3 I did these in both Megastat and in Minitab. The second of these charts for quantitative variable is the stem and leaf display. This is the brainchild again of Professor John Tukey from Princeton University, who was a pioneer in the area of exploratory data analysis. So the whole idea of stem and leaf is to break up every number into a stem and a leaf. So here I have, for example, a set of scores. Okay, exam scores are here. Should be 20 of these. Okay, and then we can arrange these in a stem and leaf display. Now, the stem and leaf that you see here resembles the histogram. It's almost like a histogram on its side. Okay, now how does that work? If you look at it, here's an eyeball. If you look at it from the right, okay, this is your view. Then you can see a histogram. How does this histogram look like? And there you go. You see that? Now, you're actually looking at a stem and leaf display for the same data. Okay, for the same data. This is for the same data. Now, the difference is that one is unordered, the natural ordering that it appears in our data set, and the other one is ordered. Now, what do we mean by unordered? The stem values are ordered. You see that 3, 4, 5, 6, 7, 8, 9. These are always ordered. We don't mix those. But the leaf values are unordered. So look at here. See, 4, 2, 6. They appear in the order, the natural order that they appear. So, for example, let's trace the 70s here. Okay, let me tidy up. And let's actually track the 70 category. So first score 78. See that? When we go across the scores of the 70s. The next one is 76. And there you go, 6. Then we come across 72, 75, 70, 77. There you go, 72, 507. You see how that works? This is what the unordered is. So it's drawn based on the order in which the data points appear in. Now we can actually turn it into an ordered stem and leaf. Now the softwares do the ordered. Okay, that's just the default for the softwares. They do the ordered version. Both of them, by the way, whether they're ordered or unordered, they give you the same impression of the distribution. Right? Both of them look like this. You see that? Now, the other thing we have is, and again, this is in the video from last chapter, I indicated these. It is possible to break these into multiple rows per stem. So, for example, imagine if I have a line that has a lot of scores in it. I'm just making up a bunch of random numbers here. 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, 0. You see that? We don't like that in a stem and leaf. We don't want these numbers to drag on for as long as they do. So what happens is we can actually break this into, let's say, 2, maybe 3, 4, depending on how long the line is per stem. So we're going to split. In other words, we can split the stem values. So here in the first one, we go 0, 1, 2, 3, 4, and 5, 6, 7, 8, 9 go here. You see that? That's how you can break it. So if you have multiple numbers, 8, 6, 7, 5, 5, 5, like that. So that's the idea of a stem and leaf. Now, remember, in this course, we rely on the software. So you don't have to do any of these formulas by hand. We pretty much do them by the software. But all softwares give us stem and leaf display. The next one we look at is Box-whiskers plot. Now, some books call them just box plots. Now, the reference to whiskers here would be because the lines that come out of a box. So here I have a box, and I got these lines coming out. Okay, so these are the two whiskers, this one and this one. That's the reference to whiskers in a box whiskers plot. Okay, so a box whiskers plot actually is also called a 5-number summary. And again, this is the idea of Professor Tukey. And his idea was that you can capture the essence of any data set using 5 numbers. So that's why it's called the 5-number summary. So what are these 5 numbers, right? The 5 numbers are minimum, first quartile, second quartile, third quartile, and maximum. Now Q1 here, Q1 is equal to P25, means 25th percentile. That means the score, so that, there you go, let's say I have, this is, let's say P25, 25th percentile of my data values. That means 25% of the scores are below it, 75% of scores are above that. And this is, let's say, the maximum, and here's where the minimum is. Okay, so that's what Q1 is. Q2 means 50th percentile. That means 50% below, 50% above, which is indeed the median. And Q3 is called the third quartile. The third quartile value is a value so that now 75% are below it and 25% are above that value. So that's what the 5-number summary is comprised of. Now, for the exams, this is what the software gave me. So the minimum is 35, max 99. So this is the minimum. That is 35, and this is the maximum. That was 99. And then Q1 is 67. Okay, so that's where this value is. See right down here, if you project it, that's 67. Q2 is the median. Median is at 77.5. That's, if you stretch this down, that's where that is. And Q3 is 91. That's where that score is, 91. Right, just to the right of 90. Okay, so that's how the software draws these, draws the box actually. That's how it's done. Okay, now what's the purpose of a box plot? Okay, so what does this box plot tell me, in other words? Well, the box plot actually gives us an impression, an indirect impression of a histogram, the distribution of data. Okay, so for example, this box plot would be that, like this, maybe something like that. That would be the possible distribution of this data. I'll show you more precisely how to do this in a minute. So let's actually do that. So these are exam scores, and I want to know what is the distribution of exam scores, right? So let's do this. Let's graph this box plot. And what we have the box plot, I mean, let's actually graph the histogram that corresponds to the box plot. Okay. Now, any histogram that's derived from a box plot is going to have 4 bars in it. Okay, and you'll see why. So first, I'm going to project these lines here, so I have the outline of my histogram. And pretty much that's where these are, right? What I'm doing is I'm aligning these with these lines. Okay, with this line, this line, this line, this line, like that. Okay, that's what I'm doing when I'm aligning them. Now, let's actually see how I'm going to draw the histogram. So this is going to be my first bar. Okay, now the height of the bar, by the way, doesn't matter. So I can go just this high. There you go. The width of it is important. The width is the length of the whisker, right? That's this length right here. Just projected up here. But the height, the first bar, is optional. You can make it this high, or you can make it this high. It doesn't really matter. Okay, so I'm going to stay reasonably low with that. Now, once you actually draw this box, the future boxes will all be relative to this, and that's why it makes it work. Now, remember, the nature of box plot, you have 25%, because this is a distance to Q1. Remember, Q1 means 25% or below it. And this is Q2, 50% below it. Q3, 75% below it. So that means each segment actually holds 25%. Right? That's what box plot portrays. Now, this is the next width, the width of the next bar. Now, imagine these percentages as the area. Like for example, this area is 25%. This area is 25%. And this area would be 20%, 25%, and this area would be 25% in our histogram. Right, these two areas right now, they don't look the same. I'm thinking about up here in the histogram, these will be 25% each. Okay, so let's do this. Now, if I'm to have equal area in each segment for each bar of the histogram, in order to achieve the same area that I'm shading here in a smaller range, right? Imagine putting all of this area into this next bar. Well, clearly if the height of the bar is this much, that won't fit, right? This is not enough to allow for this area to be contained in this one here now, right? The bar next to it. So in order to compensate for that, I'm going to make this bar higher. Okay, and there you go. That would be roughly the height of the bar. So for example, let's say if the distance from here to here, if that distance is 4 units and this is 1 unit, and this is let's say 4 by 1, this has to be a 1 by 4 to create an equal area in the bar chart, okay, in the histogram for each bar. So there you go. That's going to be my second bar now. You see that? The second bar is drawn. Now, if I look at the other 25% that you see here, right, this next 25%, and I'm looking at actually in this box now, 25%. So look at the width of this bar and look at the width of the bar next to it. Okay, well, the second one, this one is slightly wider than this one. So that means if the width is wider, the height would be shorter. So for this next bar, I'm going to go about this high. Again, this is not exact. This is just approximate. That's what the next bar is going to look like, isn't it? Let me make it like that. And finally, for the last segment. Okay, the last segment of the box. If I look at the distance from here to here, that's roughly the same distance as my second bar is in my histogram. So there you go. That's going to be almost the same distance, and it's going to be about the same height. And there you go. You see how that happened? This would be one possible histogram for this box plot. Okay, so I can from this I can decipher that. Okay, there you go. That's the distribution of this data, the exam scores. You see how you did that? Now, try to imagine this anytime you see a box plot, rather than drawing it out. If you want, just imagine what this box will look like. Oops, sorry folks, sorry, I don't know what happened here. Sorry, I don't know, something just went berserk. Okay, again, sorry about that. So I'm gonna remove that. Now next we're gonna actually take a look at a box plot from your textbook. There you go. This one is a box plot of 20 pizza delivery times. The sample of size 20 pizza delivery times. Now the values are given here. Remember the 5 number summaries. You have minimum, maximum, first quartile, third quartile, median. So this is P50, 50th percentile. Q1 is the 25th percentile, and Q3 is the 75th percentile. So those are the known values, and And that's what these are. See, Q1 is 15. So this is 15. The median is 18, so that's at 18, 22, and the maximum was 30 minutes it took for the delivery. The minimum delivery time in this sample of 20 delivery times was 13. See those 5 numbers we have? And then the box is drawn accordingly. Again, the software does it for us, so don't worry about doing this by hand. Okay. Now, what does the distribution of delivery times look like? So remember, this is a long whisker, true, right in here. The longer the whisker, right, the shorter the height. So that's going to be like the height of the bar. This bar is going to be taller. This one even taller. And this one is short, right? So it's going to be like this. Aha. That's the distribution of delivery times. You see that? So anytime you look at a box plot, you're supposed to somehow picture or overlay your own histogram on top of that. And there you go. Now, later on, by the way, some of the work that we see in inferential statistics, when we do like confidence intervals or hypothesis tests, we're going to have assumption about the distribution of the variable that we're going to consider. And for most parts, our distribution that we're going to look at in the future is this one. We're going to assume our data follows a normal distribution or a symmetric bell shape. So we're going to look at the box plot of each of these in a minute. So the takeaway from this work, this particular work, is to try to associate the shape of the distribution with the box plot. Okay. Now, this is a uniform distribution in part A. A uniform distribution is because you see that flat line, the flatlining effect here. That's what makes it uniform. Each segment holds 20%. I'm sorry, 25%. So this is a these are not box plots. We'll see the box plots for these in a moment. But in a uniform distribution, this is how they're done. A normal distribution, 25%, 25%, 25%. Here, 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 here. Okay. And this is a right skewed distribution. This one, right skewed. And we're looking at the left skewed distribution here, right? So what this graph is looking at is partitioning each of these into segments that hold 25% each. Now, for the very same, look at these without the 25% marks, but now we know that each segment holds 25%, right? We're going to look at the box plot of each of those. So look at the box plot first of the uniform distribution. In a uniform distribution, the box plot, the whiskers, same size. The width of the box here, by the way, see, all of these hold equal widths. So this is what the box look like. And this is the box, and you have equal widths, okay? And therefore, this is the box plot of a uniform distribution. There you go. Now, what about a normal distribution? For a normal distribution, because right in here, you see how the 50% are kind of here concentrated in a smaller area right there, as opposed to, let's say, 50%. Remember, this is 50%. And this is 50%. So you have 50% that are attained in a shorter range here, from here to here. Okay, so that's why the box is got narrow width, right? And the whiskers are longer here. Whiskers are longer. And that is the box plot of a normal distribution. So again, the takeaway from this, what I want you to remember is what you see in here. This one. That's what we want to really keep in mind as we go forward. And now you're looking at the box plots of a right and a left skew distribution. So look at again, this part. You see how it tapers off? Longer whisker means longer tail in the distribution. For the left skew, this is the longer tail, and this is again the tapering on the left side of the distribution. Longer tail in the distribution here means a longer whisker on the left. Longer tail in the right, longer whisker on the right. Okay, so that's what we have here. All right. Now, we also want to remember the box plot of these skewed distributions. We'll see example of these also in a moment, where we have to guess at the distribution. Now, let's take a look at this example. In this example, we're looking at the box plots for, these are actually starting salaries in thousands of dollars for a sample of 35. Business administration, this is top. These are the business people. Sample size 35. The lower box plot is at 32 for liberal arts graduates. So this is, let's say, N1. That's the second sample of size 32. So the sample sizes are decent, comparable. And this one is LA, liberal arts. Now, the question, use box plots to compare the starting salaries of business graduates and that of liberal arts starting salaries. Okay. Now, again, these are starting salaries for those two groups of graduates. Now, a picture is worth 1,000 words, right? So let's take a look at this. These are salaries in thousands of dollars. The top business, the bottom box plot for liberal arts. So first, let's look at the minimum, right? Minimum here. Let's look at the minimum. The minimum starting salary, liberal arts, 25,000. The minimum is about 6,000, 36,500, something 37 maybe even. So it looks like much better starting salary for business majors, right? Based on the samples, of course. Now, the other thing interesting is this. The minimum starting salary for a business major is almost identical to that of the median of a person with a liberal arts degree, right? That's interesting. I mean, the minimum, again, whoever is hired with a business degree, the minimum they get paid is better than 50% of the liberal arts majors, what they make or earn right in here. Now, let's take a look at what else. And you can compare the maximum, right? Look at the maximum here. The maximum is almost 50,000 versus maximum is 46,000. So you have here you have limited potential, upside potential. Here you have slightly better upside potential, right? Again, this is, we realize this is just based on these samples. The next sample may result or reveal different results. Okay. Now, and then we can compare the medians versus median. So with every aspect of this with respect to the major, it looks like business graduates do, as a whole, they're better off financially than the liberal arts graduates are. Now, something else that's important here is the shape of the distribution. This looks like a normal, right, symmetric bell-shaped distribution, right? That's what this one is. So this would be the distribution of salaries, right? That's what the distribution would be. And sorry, I know I'm trying to, there you go, this is a little better. That's what the distribution is for business majors. Whereas for this one, remember, longer whisker on the left means longer tail in the distribution. Look at that. The distribution of salaries for liberal arts graduates is skewed to the left. Again, one implication of that is the following. In a symmetric distribution, like standard, like this normal distribution, when the average looks like, because it's symmetric, median and average are about the same. So looks like 44K, right? $44,000 is on average what the business major makes. That $44,000 is a good measure of central tendency because the data bunches around that value. Whereas if you look at the median here, the mean would be less here because of the longer tail on the left. It pulls or drags the mean towards itself. But the mean would probably be something in here. Somewhere in here is going to be X bar. But because of the skewness in the data, X bar is not a true measure of central tendency. Okay, so that's the other thing that we're going to be mindful of when we look at these data. In a symmetric distribution, the measure of central tendency is a true representative of the average and something. So this is what I mean. Let's say I'm a business major. They tell me on the average, you make about 44,000. I would expect to go out, get a job, and I expect to get something on or about 44,000. That's a reliable measure because of the shape of the distribution. Okay, so there you go. Enough said on box plots. Again, these box plots, they're very important, so that's why we spent so much time on them. So in this section, we looked at the measures of, well, not measures of dispersion, but we looked at dispersion within a box plot. We looked at them in, we looked at stem and leaf displays, right? And we looked at dot plots. This was box whiskers. This was a stem and leaf. And these were the dot plots. Again, all three of these are used for quantitative variables. Okay, we don't do these for qualitative. These are displaying data for quantitative variables. All right. And with that, we're done with this lecture, with this video. Keep in mind example of these using the software. We did them for chapter 3. In chapter 3, we actually did these examples in that lecture. So that concludes lecture on chapter 4.